Nature is nonlinear. Nature is mechanics. Nature is composite. Nature is structured. In short, nature is the dance of nonlinear mechanics of composite structures. प्रकृति गैर रैखिक है, प्रकृति यांत्रिकी है, प्रकृति समग्र है, प्रकृति संरचित है. संक्षेप में प्रकृति समग्र संरचनाओं के गैर रैखिक यांत्रिकी का नृत्य है. भूमिमंगलम भूमिमंगलम उदकमंगलम उदकमंगलम अग्निमंगलम अग्निमंगलम वायुमंगलम वायुमंगलम गगनमंगलम गगनमंगलम सूर्यमंगलम सूर्यमंगलम चंद्रमंगलम चंद्रमंगलम जगतमंगलम जगतमंगलम जीवमंगलम जीवमंगलम देहमंगलम देहमंगलम मनोमंगलम मनोमंगलम आत्ममंगलम आत्ममंगलम भूमिमंगलम उदकमंगलम अग्निमंगलम वायुमंगलम गगनमंगलम सूर्यमंगलम चंद्रमंगलम जगतमंगलम जीवमंगलम देहमंगलम मनोमंगलम आत्ममंगलम सर्वमंगलम भवतु 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 सर्वमंगलम भवतु 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 सर्वमंगलम भवतु भवतु भवतु.
Good morning, everybody. Are you able to see my slide?
Good morning, sir. Yes.
Thanks, Shravan. In today's class, we will essentially introduce all the actors in our play or movie, so to speak, all the main characters in terms of who are the variables who are going to be behaving non-linearly in understanding the mechanics of composite structures, and then see the mechanics between them, that is the correlation between them, how these players or actors interact with each other, what are the equations governing their interaction. So that's essentially what we will be doing, and we'll be doing it from a broad perspective, but nonetheless we will give an introduction to the emerging techniques which are used to do this, and many of you who attended the flight vehicle structures course have seen through this a little bit, but we will give it from a slightly different perspective here, and then set up the kind of stage for the derivations to be done of each one of these equations governing the nonlinear mechanics of composite structures. Okay. So in the previous class, we understood the need for new models. We said that modeling itself is important, and the existing models have certain lacunae, and why we need to go for new models, and then we established that motivation. Now that we are motivated enough to see that we want new models, we will see what are the emerging techniques to model composite structures in particular. So the vision here is very important, because anything that you start off, you should have a certain vision of what you want to do. And then once your vision is clear, then you go ahead and declare your mission. That is, how do you want to accomplish that vision? And then you think of certain strategies by which you can accomplish that vision and mission. And then you also need certain tactics or techniques or tools in order to accomplish them. So all of these four things we will see on this particular slide. So the vision here, as it is in the case of any modeling work for that matter, is to be as close to the reality that you're trying to model. So the very fact that it's a model means that it is not the reality. There is a certain difference or distinction between the reality and the model, and you want the model to be as close to the reality as possible. But depending upon the particular application that you eventually want to put your particular model that you're going to derive into, you would see that you need not go that very close to the truth either. So how close you want to get to the truth is a very relative or subjective decision, and that is typically made based on the specific application or multiple applications in mind. And what we want to do as part of this course, and what we do in our lab as well, is essentially to enable people to get as close to the truth as they intend. And the important thing that we do in this path is to ensure that while every other modeling paradigm does this, because that's all that the model really is. If the model is not close to the truth, as close to the truth as the intended user wants it, then there's no point in having a model at all. So that is somebody, any other modeler would also have this kind of a vision. Will have a vision to go as close to the truth as the intended application is. But what is our USP in this course, AE352, as well as in NMCAD lab, which is the lab of my students and me in the aerospace department at IISc, we try to do that with a catch over there, that we want to do it with the least effort. So this is our USP. That we want to do it with least effort, and we want a mathematical guarantee that yes, this is the least effort that is possible. Well, deriving the equation itself might take a lot of time and effort, as many of my students here in the class would also vouch. But once it is there in terms of implementation, once the model is there in terms of implementing it for the actual application, the least effort would be required to actually utilize that for whatever results are to be gained with whatever levels of accuracy that are required. So that accuracy is determined by this closeness, and the efficiency is determined by this least effort part. And you would have already guessed, when we talk of the variational asymptotic method, essentially it's the variational part which ensures the closeness, and the asymptotic part which ensures that the effort is least. So let's look at it by getting into the nitty-gritties a little bit more. So this is as far as the vision is concerned. You should never lose the vision, because once you lose the vision, you get lost in the details, because it's a fairly complicated problem that we are getting into, and if you don't keep this vision in mind all the time, then you might end up doing things that will just be time consuming and effort consuming, but not of much significance. So we should always make sure that keep the end applications in mind, first of all, and they have to be kind of useful applications for a large class of problems, and once you have identified that, which is what you did, for example, in your own identification of the title, and then the abstract, the tentative abstract that you wrote tells to some extent how close you want to get to that. So that is essentially saying that what kind of a problem is it? Is it a detailed design problem? Is it a preliminary design problem? Or is it a failure analysis problem? Or all these kinds of things that we have to keep in mind in terms of how close we want to get to the truth. But the beauty of the method that we are eventually going to use is that the same method with the same starting point can usually be used in grades to get even closer to the truth, depending upon, let's say, the application changing. So you started off by deriving a model only for preliminary design, but you want to use some kind of a modified version of the same model for detailed design, then you don't need to start all the way from scratch. So you have whatever you have derived for the preliminary model, that if it is asymptotically correct, then you can go to the next higher order asymptotically correct result in order to accomplish detailed design as well. So that is the thing that one of the advantages that we have in this particular approach, that what we have done already is not lost. As long as we have defined it appropriately, then we can keep using it for other applications which are more demanding in nature in terms of a refined model. So that's essentially what the vision is. Once the vision is there, we have to next look at what is the mission, that is what you are trying to accomplish. So there are many aspects to the mission. Again, each one of your problems will involve various things, because we are dealing with nonlinear mechanics in this particular course, and in our lab we also deal with nonlinear physics or nonlinear chemistry or nonlinear science, depending upon what are the various multidisciplinary aspects that the material brings into the picture. So we would be looking at those aspects as well. So nonetheless, whatever it is, essentially we are trying to move from existing classical or linear models to nonlinear models, which means one of the mission aspects is to identify the types of nonlinearities that are of importance to a particular problem, and then see whether we are able to handle that or bring that into the modeling paradigm. So essentially there are 4 types of nonlinearities. We will see the details of that as we go forward. Material nonlinearities, geometric nonlinearities, kinetic nonlinearities, and kinematic nonlinearities. And each one of these 4 can be addressed through this particular approach through appropriate initial problem definitions, introduction of either the variational principle or a weak formulation where a variational principle, exact variational principle is not possible. And once you have all of that in place, then you can go ahead and tackle them. But being in the aerospace department, the one which concerns us most is the fact that yes, composites are being extensively used in the aerospace industry, and most of these utilizations of composites are in the form of structural components which are either in the form of beams or in the form of plates or shells. And typically these are thin sections, either thin-walled open sections or thin-walled closed sections, but essentially thin. So the fact that they are thin and also if it's a beam, it's a slender beam. Apart from being thin-walled open or closed cross-section, it's also the overall cross-sectional dimension is also very small compared to the overall length of the wavelength of the deformation typically. So that being the case, geometric nonlinearities become far more critical than material nonlinearities, because the kind of materials, at least which have been extensively used in aircraft from the composite point of view, have been polymer matrix composites. And because of the matrix being polymer, it undergoes brittle failure at about let's say 2% strain or less than that, and which basically means that the strains that we are dealing with all the way even up to failure, because most of the time we are not even dealing with failure, we are only dealing with a healthy structure, and therefore the material capability itself is restricted to about 2%, which means that with FRPs, fiber reinforced plastics, be it CFRP or GFRP or Kevlar FRPs, or hybrids of these, or sandwich structures which consist of a honeycomb in between, and then you have these plated structures being made out of these composites. In all of these situations, we find that the strain levels that you go to, whether it is the interlaminar shear strains, interlaminar normal strains, or it is the in-plane normal strains or in-plane shear strains, they are all capped by the material capability. And the material capability in turn is capped by the capability of the matrix usually, and therefore the strains that you go for maximum are about 2% or so, which is small strain. And once strain is small, the stress-strain relationship becomes linear, or in other words, a linear stress-strain relationship is a good approximation for such a situation, and therefore material nonlinearities don't play a very critical role. But going forward, we know that metal matrix composites are going to be a big game changer as far as propulsion in the aircraft industry is concerned, and many of the turbine blades and you would see that the end sections of the engine, even the compressor stages which are very close to the combustion chamber, that is the later stages of the compressor, are typically in high temperature regimes where FRPs can't be used. As of now, it's single crystal metals or metallic alloys that are used. Therefore, there is a tendency or a push to improve their efficiencies, and that is possible only through the introduction of at least metal matrix composites, if not ceramic matrix composites and carbon-carbon composites. So once we get into metal matrix composites, you will have some issues which are very similar to the metallic alloys that we were using mostly in aircraft structures, and we still use about 40% of the structural weight even in modern aircraft continues to be metallic elements, which means that the alloys, as you know, like steel or aluminium, if you plot the stress strain curve, it's not a linear curve all the way through, it goes into a non-linear regime as well. And so if you're interested in analyzing that all the way up to failure, then you do need to incorporate material non-linearity as well. Okay, so but as I said, most of the time in the healthy structure, they are operating, even in a metallic structure or a metal matrix composite, they are operating at fairly small strains, which means that a linear material model is many a times acceptable, but a geometrically linear model is definitely not acceptable because of large displacements and rotations. So you can have large displacements and rotations while still having small strains. So that is the uniqueness of aerospace vehicular structures in particular, but also most other vehicular structures where you have thin-walled shells, either stiffened or unstiffened. In either case, you would have a situation where it is geometric nonlinearity which dominates because of large displacements and rotations, while because of the kind of materials that you use, the strain still remains small, and therefore material linearity is fine. But the fact that these are beam or shell-like structures, somebody had a question? Yes, Shravan?
Yeah.
Yes.
Yes.
Go
I
ahead.
have a
Yeah.
question.
Yeah.
Sir, I don't understand that materials can have large displacement and rotation, but a small strain. Can
Okay.
you give an example so that
Sure.
I can
Sure.
understand it better?
Yeah. So let's take an example of this aircraft. Can you see this now, Shravan?
Yes.
Yeah. So suppose I apply a load which is typical of the aircraft, let's say lift distribution, then you would see that there is the tip displacement that you have over here is fairly large, and the cross sections also rotate by a fairly large amount, where you can't, for example, approximate the rotation theta by sine theta for that matter, or tan theta for that matter. So similarly, the displacements are also fairly large. If you have been observing while on an aircraft the actual takeoff and landing, you would see the amount of deformation that the tip goes through. You can actually, with the naked eye, it is possible to visualize the kind of displacements and rotations that are there at the tip. The reason why that the wing still doesn't fail is because the strains still remain small. How does that happen? Essentially, you have the, for example, in this case, the example that I'm demonstrating is a bending example, right? So this bending example involves certain rotations of the cross section and the displacements along this, which is, you can think of this as, let's say, the Z direction. So therefore, the displacement along this, if we call it as, or let's say X3 direction, and therefore the displacement along this is U3, then you would see that U3 is very large, and dou U3 by dou Y, where Y is along the span-wise direction, that is also very large. So these two are very large. U3, that is the displacement as a function of Y, or let's say X2, and then you also have the derivative of U3 with respect to Y2, that is U3 comma 2, is also fairly large. So these two are large, and they both contribute to a strain which is gamma 11, that is along gamma 2 2, which because if you want to introduce it, let's say along the span, which is let's say the x2 direction, then you have the strain along the span direction, which is an bending strain, part of which is under compression, that is the top surface, and the part of which at the bottom, which is under tension, right? So now these strains are related to the displacement U3, but what you have is not U3 itself, but dou U3 by dou x2. So we have introduced x2 coordinate along the span. I'm using the usual coordinates that I used with an aircraft, which is x1 along the fuselage, x2 along the span, and x3 is perpendicular to that plane, right? So now what I'm talking about is the strain gamma 2. Let me write it down. Gamma 2, which is caused by your this is okay. We'll go into the nonlinear definitions of these strains later, but for now, essentially this is basically your dou U2 by dou X2 if it were linear, right? So even in this linear definition of the strain displacement relationship, you can see that if U2 is going to be large, then you could still have the X2 dimension so large that your derivative of U2 with respect to X2 still being small. So that is essentially what is happening. So the fact that you can have a large numerator, but the denominator also being so large that the fraction still remains small. So that is essentially what is happening over here. So ignore the coordinate systems. It's a little confusing for what I mentioned over here. But if you take a, let's say, typical beam like what you see over here, and then you're basically introducing an x2 coordinate system over here, and then you have in this direction there is a certain load that is there, and let's say this is x3, and then you are basically having a strain at any given point. You're having a strain which changes linearly with respect to the cross section about the neutral axis, which is essentially your gamma 2 strain, which is what we are talking about this. And this U2 in turn is related to the U3, which is what I was describing to you as very large. And therefore the rotation that is involved also contributes to this strain, as you know, in the bending equations. The reason why I don't want to write all that is because those are all approximate relationships which we are going to give up and go into a new paradigm. But just to make you understand based on what you already know, this suffices the fact that U2 can be large, but because x2 is also large, therefore you are going to have the fraction still being small. So does that convince you, Shravan?
Yes, and additionally, sir, since when you were explaining it, I struck with a thought that when this wing, it's being getting deflected, it's not getting deflected permanently. So
that's
as a result, we may say that the strain is not there because the wing is kind of getting back to its original position.
That's a different thing. That is to do with elasticity. So there are two aspects to this. One is you can have elastic and linear, or elastic and non-linear. You can have inelastic and linear, and inelastic and non-linear also. So all these four combinations are possible. We're not talking about the elasticity, but what you're saying is absolutely right, that this material is also elastic in the sense that once this load is removed, it goes back to its original configuration. But that does not have a direct impinging on what we are talking about linearity and non-linearity. which is essentially talking about between two of the players that are involved over here, which is in this case the geometric nonlinearity is what we are talking about, the strain displacement relationship. So you have the relation between gamma 2 which is a component of the strain, and u2 which is a component of the displacement. So the relationship between gamma 2 and u2 is as written over here is is linear, but then you also have a term half of dou u2 by dou x2 whole squared. So that is an additional term which is going to make this relationship nonlinear. Whether to have that term or not depends upon whether that additional term is as big as the existing term or is of comparable significance, which basically means that you should have large rotations, because dou u2 by dou x2 essentially is talking about a particular kind of rotation that is involved over there, and you are essentially trying to see how u3, that is the deflection perpendicular to the span-wise direction, that is along the if the aircraft is let's say cruising level flight, then it's the upward vertical direction. So that u3 and its derivative, which is essentially the rotation, that is going to cause u3 as a derivative with respect to x2, that is essentially going to cause a rotation, and that rotation is fairly large, but still the strain that it causes continues to remain small. That is essentially what is happening over here. Okay?
Okay, thanks for the explanation, sir.
Okay, so let's get back to the mission over here. Vision is very clear. We want to enable not only ourselves who want to utilize the model, but once we have the model in place and we have published it, like how you're all going to publish your papers, then it is available for the entire community to utilize. So for every one of them who's going to eventually utilize it, whether they are in the industry or whether they are in academia or any other kind of research activity, when they are going to utilize it, they want to get as close to whatever the reality, real problem that they are modeling. It could be a flight vehicle structure actually flying, or it could be a specimen in the lab that they are testing that it has to be applicable to. So they want to get as close to that truth as possible with the least effort. That being the requirement or the vision, what is the mission? So that is accomplishable of getting as close to the truth only if you are willing to move away from your comfort zone, and the comfort zone essentially being the linear models that we are familiar with, the classical theories that we are familiar with, like the Euler-Bernoulli model for beams and the Kirchhoff-Love model for the plates or shells. So now we want to go a step beyond that, which means that essentially there could be other complications which are setting in as well, but the most important one is that when you're moving from the classical to the non-classical is the non-linearities which occur. And a specific type of nonlinearity becomes very critical for aerospace composite structures, and that is basically what appears as a geometric or what in reality is a geometric nonlinearity at the 3D level. When you're modeling the entire structure, be it a wing or any component of the wing, as a three-dimensional structure, letting all three spatial variables x1, x2 and x3 to be independent variables, and we want to derive everything as a function of x1, x2, x3, either analytically, semi-analytically or numerically. That is immaterial, doesn't matter. So what really matters is that we are trying to get everything, whether it's the stress or the strain or the displacement, all these fields, we are trying to get it as a function of all the three spatial variables. So that's a 3D model. So now in that kind of a 3D sense, what you have is a geometric nonlinearity, even in the example that I just described of the bending of the wing. But when you try to reduce this, because in this case, for example, it's a fairly thin structure, this wing, and compared to the chord of the wing. So of course it goes to a very small value over here and a large value over here. But if you take an average, because it's tapered wing, and if you take the average value, you'd still see that the thickness of the wing, this is a 2-scale model, a 1:400 scale model that you're seeing over here, and therefore you can see that the maximum thickness to chord ratio is of the order of 10% or not more than that. It could be even lesser. So essentially what you're talking about is a good case for if it's a static deformation at least, or low frequency vibration problem, then a shell model is good enough. So you can go from a 3D to 2D. In other words, the explicit dependence on the x3 or the thickness direction coordinate is no longer necessary. You only need to have it as a function of x1, which is along this, and x2, which is along this, and therefore you can deal with it as a plate or a shell. Or you can deal with it as a beam as well, because the cross-sectional dimension, even at the maximum location, is fairly small compared to the span, that is the length of the cantilever that you see over here, which is 1/2 of the wing. So in either case, we are doing what is known as a dimensional reduction from 3D to 2D if it's a plate or shell, and 3D to 1D if it's a beam that we are trying to model. So a geometric nonlinearity is what we started off with in the 3D, but magically it gets transformed into a nonlinearity in the 1D or 2D constitutive law, that is the stress-strain relationship. But we know that if it was a 3D stress-strain relationship which was nonlinear, that is what we call as material nonlinearity. Now, we didn't start with the material nonlinearity because we are dealing only with FRPs, let's say, and therefore, and even if we are dealing with metals, we are saying that we are not loading the structure so much that the stress and the strain are within the linear limits. So therefore, we are saying that the material nonlinearity is not there in the 3D. But in spite of that, the very fact that there is a geometric nonlinearity, it gets transformed into a pseudo-material nonlinearity, or what we call as a physical nonlinearity or a non-classical nonlinearity at the dimensionally reduced models. Either it is the beams 1D model or a plate or shells 2D model. In either case, what we are having is a dimensionally reduced model with a nonlinearity not only in the geometric sense, that is its strain displacement, 2D strain to 2D displacement, that relationship of course is nonlinear, but in addition the 2D stress to the 2D strain also becomes nonlinear, or the 1D stress to the 1D strain also becomes nonlinear. So what we mean by all of these, we will get into the details as we go forward, but those of you who have attended the flight vehicle structures already have a taste of what we are talking about. So let's talk about the mission now. We want to understand essentially something beyond the existing models, which are shown to be having certain lacuna. In fact, we listed out 5 or 6 different problems or issues with the existing models, and which is why we wanted to go for a new model. And that new model is what we are calling as a non-classical model, which is able to take care of certain phenomena that the classical model was not able to, but which are observed in reality, either in the flight or in the lab experiments, or some things which may not yet have been observed but still might be equally important and may probably be observed if the right kind of experiments or right kind of sensors on the actual aircraft were to be utilized. It might be happening and without even our knowledge, and I gave you examples of health issues also which could be something similar to that. But in this vision, the first step that we want to do is to go towards a newer model, which means that we want to better understand such phenomena which are not already understood with the existing models. So which in turn means that we have to get what are essentially both high fidelity as well as high efficiency models in a simultaneous sense. A lot of people working towards high efficiency models without looking at the fidelity aspect, and others who are looking at only improving the fidelity or accuracy, in other other words, but not worrying about the computational efficiency, saying that anyway computers capabilities are becoming better and better, both hardware and software, and therefore there's no need to worry about efficiency. So there are these two schools of thought, whereas our school of thought is to ensure that for whatever level of accuracy, whatever level of fidelity hi-fi model that we want to have, for that hi-fi model we want to ensure the highest possible efficiency from a mathematical guarantee point of view. So that's essentially what we are trying to do. This this adjective simultaneously is very, very critical over there, because there are two aspects to it, and we want to make sure that both of them are catered to. So, which means that we need improved analysis and design techniques, both for current operations as well as future applications that we might have for various kinds of new design paradigms that are coming forth, like blended wing body design, or all kinds of applications for, let's say, operations on other planetary bodies of vehicles, not just rovers on the surface, but also which can fly across, which could be amphibious in nature in terms of having motions possible in multiple sense, both traversing the planet's surface as well as flying in the atmosphere over there, in spite of the different chemical compositions that those atmospheres might have, the different densities and pressures and temperature ranges that they might have, etc. So in all of those kinds of situations, what kind of mechanical and non-mechanical requirements that might be there have to be taken care of. So we are interested in understanding some of those futuristic applications as well, apart from many which are of current requirement itself. And the current requirement itself is humongous in terms of the room for non-classical models and non-linear models, leave alone the futuristic applications. So this is as far as the mission is concerned. So now that the vision is very clear, the mission is also in place. Yes, Shravan?
Sir, does design techniques here refer to what do you call advanced manufacturing techniques?
Not necessarily. It's one step before that. So we are, but modeling is also useful in manufacturing parlance. So it's good that you brought up that aspect to it. But even if you're not concerned about manufacturing at this stage, the very aspect of designing something, eventually you want to manufacture that. But even in the design process itself, a mathematical model is very helpful, as we saw in the previous class, where we are saying that we are going to do the model entirely on the computer. It's essentially a CAD model, a computer-aided design that we are accomplishing, right? So that CAD model also requires us to understand many of these nonlinear and non-classical phenomena and incorporate them appropriately, and at the same time ensure that just because we are analyzing them doesn't mean our model is going to take much longer time. Yes, it's going to take longer time than the linear or classical model, but the additional time that it takes should be worthy, in the sense that whatever additional information that you're getting from a non-linear, non-classical is useful. But then, yes, that same CAD model is eventually going to be useful for a CAM model, where you're going to look into what is known as process modeling. So that's going to adds a lot more value than what the CAD model by itself is going to do. The CAD model is just going to give you the sizing and the shaping and the choice of materials that you're going to use in various components or sub-components. But then eventually you're going to realize that as a physical hardware, that's where manufacturing comes in, whether it is through the conventional, traditional subtractive manufacturing, or through what's becoming more and more common in terms of additive manufacturing today. So either case, there is a certain process which is involved. For example, most aerospace composite structures are made using autoclaves. So that autoclave process of putting the wet pre-preg materials after it has been laid up either through hand layup or any other automated layup systems. Once you have laid that up, it could be a fiber, let's say fiber winding kind of a situation, automated or whatever. Once it has been done, it's still wet and it is put into an autoclave and goes through a certain cycle of temperatures and pressures before it gets cured. Cured in the sense that it becomes usable. That is, it's no longer a wet composite. It is the composite structure with the kind of strengths and stiffnesses that you have designed it for the actual application to take forward. So that time period in which it is within the autoclave going through these, if you plot temperature versus time or pressure versus time, and there are certain cycles that it goes through, all of that, how it changes the mechanical properties of this wet pre-preg that you put in the first place, how slowly that wetness is getting removed and it's becoming a cured composite with the desired strengths and stiffnesses. That process requires a certain modeling itself. So there is a process modeling that is involved, which becomes one of the important components into the manufacturing. So if, we are not getting into that aspect as far as this course is concerned, because that's an entire topic by itself, and it's more in research stream rather than as a course or a teaching kind of a stream, because there's so many things which still need to be understood in terms of how the actual process takes place. There are certain approximate models already in place for process modeling, and there are a lot of papers, research papers in this domain as well. But if you're interested in terms of the manufacturing techniques, improved manufacturing techniques, then you do need to get into that process modeling as well, apart from the structural modeling. Okay.
Thank you very much, sir.
Yes, sure. So now we have looked at the vision. We have also looked at the mission. The next thing that we want to look at is the strategy. How do we go about accomplishing all of these, and with the final goal being the vision that we have. So for us to accomplish that vision and mission, we need a certain strategy. So even when you're going to a war, let's say the military, whether it's the Air Force or Navy or the Army, it has a certain strategy and it also has certain tactics. So we are not talking of the tactics yet. That's more of short term, how we are going to exactly accomplish that. But this is more in terms of the overall strategy for the entire war, or let's say a battle as part of that war. What is the strategy that you're going to take forward? So that's essentially what we will see now. And the main strategy we have here, because our application is motivated from the aerospace application, be it for an aircraft, helicopter, launch vehicle, or missile, satellite, it doesn't matter. Whatever it is, we are looking at modeling composite structures for this, at least the existing composite structures, which are all fiber reinforced plastics, and where material nonlinearity doesn't play a very critical role, but geometric nonlinearity plays a critical role. The reason being that the displacements and rotations are large, strains are still small, and the fact that the displacements and rotations are large is because of the fact that you have shell-like structures or beam-like structures, and they are multiply connected in various ways through various joints or bonds, adhesive bonds, rivets, etc. But essentially, if you look at each and every one of those components, they are either having one dimension very large or having one dimension, which is the thickness in this case, very small. So you can deal with them either as a 1D beam or a 2D plate or shell. So essentially, geometric nonlinearities at the 3D level are very, very significant. Material nonlinearity at the 3D level is not so significant. So that being the case, we want to see how both of these can be considered, because there have been Shravan's own advisor at SNU, his PhD thesis was entirely, Professor Burela Ramesh Gupta, his thesis was entirely on the hyperelastic materials, and the hyperelastic materials are materials in which the strain can also be large. So it's not only the displacements and rotation, the strain also can go to large values without the material failing, and therefore how do you deal with them? That can actually be done using models using the variational asymptotic method. So it's not that we have not applied the variational asymptotic method to materially nonlinear problems at the 3D level. We have, but it's the number of applications for such materials in a typical aerospace structure, at least as of today, is not way too many, and therefore maybe you could use it for tire modeling. In the landing gear of an aircraft, you would have the tires which are made out of essentially rubber-like materials, though they are of course reinforced with nylon or steel or even composite fibers these days. You would have these matrices that essentially in the tires are going through fairly large strains, and therefore even at the 3D level, the material nonlinearity becomes important. So we have to take care of geometric nonlinearities, we have to take care of material nonlinearities, but most significantly for aerospace structures, we have to take care of what are known as non-classical nonlinearities, which is essentially an evolutionary interaction between them. That is, what starts off at the 3D level as a geometric nonlinearity becomes a pseudo-material nonlinearity, or what we call as a physical or non-classical nonlinearity, and that evolutionary interaction plays a very, very critical role. And if you don't take that into account in the 1D model, you say that anyway I'm dealing with linear materials or materials which do not go through very large strain because I'm dealing with the healthy structure only, so therefore I will not deal with stress strain nonlinearities even in a beam model or a shell model. Then you're going for a toss, because there the stress-strain relationship in the 1D or 2D model becomes nonlinear in spite of the materials being used being 3D linear in essence. So this is something that many people are not familiar with because that, for example, in civil engineering structures, etc., we are typically using short stubby beams or columns where material nonlinearity is the only reason why a beam or a column model will, or for that matter, let's say a ceiling, it's a plate kind of a model, only reason why a beam or a column or a ceiling or a plate model in civil engineering structure could have nonlinearities in the stress-strain relationship at the 2D level or 1D level is only because the material could have been nonlinear, or the loads were so large that it went into the nonlinear regime. But here, in our case, in the aerospace structures, we are dealing with very thin shells or very thin-walled beams, open or closed cross-sections. But the result is that even when we have material linearity at the 3D level, at the 2D or 1D level, we are having pseudo-material nonlinearity. And that is what is going to be most critical, and you would see the effects of that as we go forward in some of the actual examples that we will take up in the future weeks. So now we are done with the strategy. Now we're going to the tactics, and this is what are the tools, and that's what distinguishes us human beings from the rest of the living kingdom, whether it is plants, trees, or animals. The only reason they have probably not been as successful as us in terms of improving ourselves is because they do not use tools, and we use tools. And that's why animals which are probably otherwise much more powerful and stronger than us, like an elephant or a tiger, can still be kept in zoos by human beings or used for various purposes. The only reason has been in the human ability to use tools. And so these tools or techniques become very important. Otherwise, all of these are four important pillars: the vision, the mission, the strategy, and the tactics that you have. But those tactics whereby you're actually deploying your tools, deploying your weapons or techniques that you want to actually engage in a particular battle, that's what makes us so much more powerful. So any one of these missing means that there is going to be an issue. And this is not only from this course point of view or our approach to nonlinear mechanics of composite structures, but any other problem that you undertake, whether it's for your paper that you're writing or any other course that you're doing or in your career, etc., you should have all of these aspects to it. And many a times we have them, but it's just that there's no clarity about that, and it's all kind of blending into each other in some way, and therefore we really don't see the purpose of what we are doing. So if we want to do that, we have to be very clear about what's the vision, what is the mission, what is the strategy, and what is going to make that implementation possible, namely the techniques or tactics or enablers or tools that we are going to talk about. So what is the tool that we have over here is essentially a state-of-the-art mathematical approach that we will take. Essentially the variational asymptotic method, that's going to be our main weapon with which we are going to progress. But a single weapon army or air force or navy is not going to in most situations win the battles for us. So you need multiple weapons, and each of them have their own purposes, and that's what we will list out in this particular slide. So as I said, the variational asymptotic method is by itself not actually a single weapon, because it involves the V and the A. So it's actually two weapons combined into one, where it's like a two-in-one kind of a weapon. One ensures the high fidelity that we were talking about. The other ensures the high efficiency, computational efficiency that we wanted to engage in. So that's what the variational and the asymptotic aspects of the variational asymptotic method do. But essentially it's a single tool, it's a single weapon, it's a single enabler, which is state of the art. But we have seen that if you want actual real life implementations, then by itself, yes, it can go a certain level of applications. But if you want to enhance the range of applications that you want, then you would, Yes, Kedar?
Hello, sir.
Yeah.
So you mentioned about modeling of hyperelastic materials using VAM approach, right? So in that we have multiple modeling techniques, right? For example, a neo-Occhian or MR model, or more advanced models like Mooney-Rivlin or the further models that are present. Can we model all of them using this approach? I mean, the variational
very good question. And in fact, Professor Ramesh Gupta's thesis looked at neo-Hookean and Mooney-Rivlin models and certain hyperelastic models for anisotropic structures as well, which are like composites having properties in different directions. But if you're talking of more advanced models like the Ogden model, etc., you should keep in mind the main requirement of VAM, whether it is for hyperelastic application or any other new application that it has not been put into earlier on. There are two requirements for us to be able to apply VAM. One is to apply the V part of it, we need a variational principle governing the science or physics behavior. In most cases, it's just mechanical behavior. For example, if it's a hyperelastic behavior, we're not interested in other branches of physics or science. We are only interested in the mechanics aspects. Does the mechanics of that hyperelastic material have a certain variational principle governing it, and more often than not, even with the more complicated models like Ogden's, etc., it is possible to in the original form it may not look like let's say a variational principle. It's more from a classical mechanics point of view of Newtonian mechanics, where it's essentially an equilibria that is being understood at the stress strain level or at the lower length scale level of the material that we are talking about, and therefore it involves a certain stress strain relationship which is nonlinear. But it's possible to introduce a concept of the strain energy which is stored in the material, because it's a elastic material, and elastic strain energy is something that is easy to incorporate. All that you have is the strain energy density, that is energy per unit volume of the material, is given by the integral of sigma d epsilon dV, integrating over the entire volume that you have, and sigma double dotted with d epsilon, where sigma and d epsilon are both second rank tensors and therefore involve their own components, and therefore what you're ending up is a scalar quantity which is a strain energy, which is what you're trying to minimize. So as long as you're able to put it into that form, whether it's a hyperelastic material or any other material, or not even a structures problem, any other problem in engineering can be tackled using variational methods. For it to be able to utilize asymptotic methods, which is another branch of techniques, you should have certain small parameters in the problem definition. You're not making wrong assumptions or wrong approximations and just for the heck of applying the asymptotic method, assuming something to be small, but the very problem definition itself, like for example in this case the cross-sectional dimension to the length, or in the case of a plate or shell the thickness to the other dimensions, or in both the cases the kind of materials that we are using, the maximum strain that they can undertake before material failure sets in, because those materials are capable only of, let's say, 2-3% of the strain, etc. So all those are bringing in certain small parameters. In a sandwich structure, the thickness of the face sheet to the overall thickness, or the core or the foam or the honeycomb that you use in between, its mechanical properties vis-a-vis the mechanical properties of the face sheet could be again another small parameter. So there are many different small parameters which can come from the geometry governing the structures that we are interested in and the materials that we are interested in. So in the case of the hyperelastic material, the only difference comes in terms of are you able to put it into a variational form. Therefore you can use variational principles. Can you use it in the form of with asymptotic techniques? You can, if that hyperelastic material that you're going to be investigating is the structures that you're interested in considering are plate or shell like structures or beam like structures, then yes, though the strain is not small, because those materials can go all the way up to 400-500% strain. In other words, the original length, 5 times that length you can stretch it to, and still it is within its failure limits, it's still within elastic limits, and when it comes back to its original shape and size. So in such materials, yes, it is possible to bring in a variational principle, but strain no longer is a small parameter, so you can't use asymptotics in the sense of small strain, but you can still use asymptotics in the sense of you have made a beam out of that hyperelastic material, or you have made a shell out of that hyperelastic material, or a stiffened structure which involves both a beam and a shell out of that. Then in all those cases, from the geometry of the structure that you're going to analyze, you have small parameters. So it doesn't matter where that small parameter is coming from, but as long as you have a small parameter in the problem definition, you can still utilize that and come up with the variational asymptotic method for it, because variational the existence of a variational principle ensured that you can use variational methods. The existence of small parameters ensured that we can use asymptotic methods. What we need here for applying variational asymptotic method or VAM is both these conditions to be satisfied simultaneously. That is, there has to be a variational principle governing the signs or behavior of that whatever materials or structures that you're going to analyze, and you should also have small parameters in the problem definition. And if you do have both, then why not? You can have even Ogden kind of models. It's not as simple as or easy as probably dealing with a Neo-Hookean or a Mooney-Rivlin kind of a model, but yes, you can deal with that as well, because in the case of Neo-Hookean or Mooney-Rivlin material models, which are typically applied to materials which are capable of strains of the order of 20%, 30%, etc., but not, let's say, 400, 500%, where more advanced hyperelastic material models like the Ogden model are essential. Then you have to give up on even a moderate small parameter like the strain there and then go for it. So the derivation becomes a little more tricky and a little more involved and complicated, but it is definitely feasible. You can still do it. Does that answer you, Kedar?
Yes, sir. Because I had in my mind of applying this VAM analysis to the skin kind of materials back in the days. So let's see.
So if you have a skin kind of a material, then structure, then you have the thickness to the other dimensions being small parameters. So as long as it's not going through very high frequency vibrations or very high frequency dynamic loads, then you can still hope that you can use it as long as the material model is conducive to being applied in a variational sense. And you have, if you're familiar even a little bit with finite element analysis, you know that weak formulations like the Galerkin methods are usually already there, very well established, or even the Rayleigh-Ritz approach, etc. These are all energy approaches where you know that there are certain approximations which can be done where exact energy principles may not be applicable or might be too complicated to deal with. Then you can still deal with these weak formulations. So even when you have such weak formulations, you still have a variational principle to go for. So as long as that is a reliable weak formulation to have, then you can definitely apply the VAM, and it will definitely improve the computational efficiency of the model while retaining the accuracy, unlike any other approach that you take.
Sure, thank you.
Okay, welcome. You can lower your hand. Yeah. So, as I said, VAM is not the only tool that we have on hand over here. We have other tools which go along with it and make the same purposes that we have talked about in the mission strategy, etc., still accomplishable or better accomplishable or more easily accomplishable. In other words, even lesser effort, or it has to be even more accurate. So either one of these is what we are trying to do by adding more techniques to this in addition to VAM. And so one of them that we incorporate is what is known as the non-deterministic technique. So most of what we have learned in undergrad at least are deterministic techniques where we know, let's say for example, the Young's modulus of the material. We know the Poisson's ratio of the metallic material that we are dealing with for a given specific value, let's say 210 gigapascals and 0.3 as the Poisson's ratio. We have these values and we go ahead and do the entire problem analysis or design with these values. But what if there is a little bit of scatter in that? What if these values are not fully reliable? There is a certain probability that they can be slightly different from the value that you have taken. Then in a linear model or a classical model which is linear, you would have no issues because you can directly go and take the appropriate fractions of how much it changes. You can say that even if it has a probability probability density distribution function, you would see that the end results, let's say displacement, in the case of a aircraft wing, the tip displacement is what you're interested in. That tip displacement under a given set of loads will also go through a very similar probability density distribution function as your material properties do. It's just a scaling factor that you have to apply depending upon the mathematical model that you have. So there's not much of a problem. But here we are dealing with nonlinear models, and when you're dealing with nonlinear models, the probability density distribution function for the tip displacement or the maximum stress occurring at the root on the top or the bottom surface in compression and in tension, those values of the stresses or the values of the displacement or the value of the strain somewhere, or the potential for failure, all of these are also probability density distribution functions, which will have entirely different shapes from the probability density distribution function for the carbon fiber and or the epoxy matrix or the carbon fiber epoxy combination as a CFRP. Even if you have the probability density distribution functions for them, the end results PDFs might look very, very different from the PDFs for those materials because of the fact that we have a nonlinear model in place. And therefore, the processes through which all of these go through before the end results of a tip displacement or a stress at a particular point or a strain at a particular point or the potential to fail, all these are derived through various levels of nonlinearity, and therefore you need to incorporate these non-deterministic techniques up front. Again, Professor Berdychevsky himself has done a lot of work towards this. I mentioned a few of those as we went through. Professor Guru Prasad at IIT Bombay, he does a lot of that. Professor Murugan, who is in IIT Madras now, Sendil Murugan, who was my PhD student in the past, he has done more from the Monte Carlo simulation point of view. So there are many ways in which these non-deterministic techniques can be applied. The Monte Carlo simulation is more of a rough and tough application of that, whereas Berdychevsky's techniques, which you will see parts of that in the book that I've mentioned as a reference as well, you would see there's a much more kind of intelligent way of approaching the problem, where you're not just doing it in a number crunching kind of a way just because you have very good computational hardware and software. You are going to understand it from a fundamental perspective, and that is also possible by using non-deterministic techniques in an appropriate sense. But essentially what this is going to do is it is going to increase the effort. So this least effort that you have is going to suffer a little bit, but yes, you are going to get much closer to the truth, which you would not have without that. And therefore, that being our primary requirement, that we need to get closer to truth, but still because we are using the A part of the VAM, we are still, even with a non-deterministic technique, we are still having the lesser effort than what would have otherwise been achieved. So that is essentially what deterministic or non-deterministic rather techniques does to us. It basically does this high fidelity is ensured even more than what it was only through the variational principle. The variational principle ensures high fidelity to some extent, but that's based on a model which was deterministic, given specific values for the material properties. Similarly, even the load distribution may not be known in a deterministic sense. The lift distribution that the aerodynamic team that gives us the lift distribution or drag distribution or the pitching moment distribution, etc., they also have a certain uncertainty which is involved with respect to those loads. Similarly, the other loads as well. So those uncertainties or the manufacturing techniques, even though they are improving quite a bit, there can be certain tolerances that are associated with the manufacturing technique in terms of the geometric values of the thickness, etc., So those properties, then the joint properties, many of these will have a certain scatter which are best taken care of by using statistical parlances like probabilistic techniques or non-deterministic techniques, and that's where this comes in at improving the accuracy even further. Then the third way in which we increase or enhance the accuracy is by doing what is known as the concurrent multi-scale modeling. We will see that in the traditional approach, composites are taken care of usually in 2 steps, sometimes 3. The 2 main steps that are involved is the micromechanics, where you know the fiber and matrix properties. Using that you get the layers properties, and using that layers properties you understand the structures properties. In between, of course, you go lamina by lamina to laminate and then to the structure. So this is essentially 2 independent things that are done, micromechanics and macromechanics. But here we do what is known as concurrent multi-scale modeling, that is the different length scales that might be there, and in a dynamics problem it could be different time scales that you're dealing with. In the same problem there could be certain loads which are high frequency loads and certain loads which are either static loads or very low frequency loads. So both of these effects could be happening simultaneously in the behavior of the structure, and because it's a nonlinear model, principle of superposition won't work, so you can't deal with each one of these loads separately and then put the results back together, stitch them together again. So you can't do that. If you do that, you will get results which are not very accurate. So essentially you have to deal with multi-scales either in length scales or multi-scales in the sense of that time scale as well. So in either one of those, most people, the way they do it is to do it in each one of these scales separately and take the information from one to the other. We want to take information 2 ways, that is not only from the lower length scale, that is the fiber matrix level, to the actual structural level, but also back from the structural level to the fiber matrix level to understand more complicated phenomena like the fiber matrix debonding or the fiber breakage or the matrix cracking, which are happening at a lower length scale, and that cannot be done with the equivalent homogenized structure that we are going to deal with for the laminate or for the overall wing structure or a wing spar or any one of these things. So we have to come back at least at those locations which are of critical nature. For example, in the case of stresses or strains or failure, it would be the points on the top surface or bottom surface close to where the wing is attached to the fuselage. Those could be the danger areas, and at least in those locations for small points around chosen points, very small areas or very small volumes, we would like to do a more detailed analysis of not an equivalent homogenized structure but of the actual fiber and matrix and the interface between them, etc., using cohesive zone modeling, etc. So there we need to come back from the larger length scale of macromechanics to the lower length scale of micromechanics, and that's what this concurrent multi-scale modeling is all about, the ability to go back and forth between these 2 different length scales or time scales. And what that does, of course, the concurrent multi-scale modeling also is very similar to what the non-deterministic technique does. That is, it essentially is improving the fidelity levels and is therefore getting closer to the truth. But it does put a spoke in the wheel in terms of the efficiency and the least effort. But we have put that least effort with a catch there, that we want to get as close to the truth. For that level of accuracy, what is the least effort? And that still remains because of the asymptotic nature of WAM that we are still incorporating along with non-deterministic techniques, along with concurrent multi-scale modeling techniques. So these 2 are further increasing the accuracy over and above the variational principles accuracy itself, and bringing in a certain penalty in terms of the computational efficiency, but we are still willing to live with. So the fourth tool or fourth technique that we use is something that will bring back the efficiency, at least by some extent, in spite of using these more time-consuming second and third tools. The fourth tool does something very similar to what the asymptotic does in terms of the end goal, that is improving the efficiency or doing it with least effort. And that's what is called as the technique, very well established technique in various other domains of what is known as the nonlinear domain decomposition. So that is basically the overall structure that you are having, let's say the entire aircraft or the entire wing that you're dealing with. It has so many different components, and non-linearity may not be important everywhere. There might be certain components where non-linearity is more important than the others, because there could be certain components which are thicker in nature, or there can be certain components which are stubbier, where non-linearity may not play a very critical role. So why force the non-linear model on those as well? Can you use an automated process or a mathematical process or computational algorithm by which you can identify which domains are the ones where nonlinearity is important, where nonlinearity is not important, and therefore apply it appropriately. So that is the nonlinear, the approach of nonlinear domain decomposition. And then eventually you are applying the appropriate boundary condition between those components to blend them together. And it's not that you're solving each one of them separately, but right up front in the overall problem model, you are bringing into a picture for various subcomponents, various kinds of models that might be more applicable, and therefore you are dealing with it. Even in the sense of, let's say, the hyperelastic materials that Kedar talked about. Suppose you have, or Shravan was interested in, you have, not all the materials could be hyperelastic. There could be a certain component, for example, when you're dealing with the landing gear, it's mostly made out of steel, and then the tires are made out of hyperelastic rubber, along with various reinforcements which are again not hyperelastic probably. And then you are dealing with this entire subsystem or component. Then you are actually dealing with some places where material linearity is okay, and some places where material nonlinearity has to be accounted for. So then you are basically using these kinds of techniques like nonlinear domain decomposition to let the computational algorithm or your code itself automatically determine where all these are important, where it is not important, based on the material models that you're giving for each one of these, and then the appropriate way of interfacing these different kinds of material models and still work out the solution. So this fourth tool or technique that we have over here is essentially improving the efficiency or the least effort principle that we want to also ensure, apart from the accuracies. So is this clear? Are there any questions or doubts so far? Okay, thank you. So let's go ahead, and we may not fully complete this slide, but we'll come back to it later. Many of you have seen this particular slide as part of the flight vehicle structures course too, but it's important that we revisit it, and a few other additional information will be given here. So those of you who have not attended the flight vehicle structures course or missed this particular lecture when I talked about it, please do go ahead and take a look. I don't remember the exact lecture number for this, but should be in the first half of the course, where we talked about these things. And this is very, very important, because most people make assumptions without even understanding the implications of those assumptions, just because somebody else is making it, or just because without that you're not able to solve the the problem. So there are two questions that one needs to ask before you choose to make certain assumptions and take forward in your actual implementation, whether it is in terms of deriving your mathematical model or eventually then applying it for a particular problem of analysis, design, etc. So the first question that you need to answer is that whether the assumptions are necessary in the first place. That is, maybe you can still solve the problem almost as accurately and as even more importantly as efficiently without even having to make that assumption. And very funnily, some of the classical models, people have made certain assumptions that are not even necessary. Without that, you can still derive the same equations. And the classic example of that is the Euler-Bernoulli beam theory. Some of the assumptions that they have made are not even necessary. Even without that, the first approximation that you would get in variational asymptotic method is that model itself. So it's not at all necessary to make some assumptions, but still people make it and go forward. Whether that assumption is true or not can actually be indicated by the variational asymptotic method rather than having to make that assumption and then derive the whole problem and still not being sure whether that was essential or not. So when in doubt, just give up that assumption and see if you can still work it around. If there are issues, then you have to go back and explore. Maybe that was a necessary assumption, otherwise the mathematical tractability of that problem might be under question. It may not be tractable and therefore you may not reach the solution. So as far as possible, reduce the number of assumptions that are involved and take them only if they are necessary. And still, even if they're necessary, but if they're not relevant, again, it serves no purpose. So you might just be doing an academic exercise of deriving something which is not of much utility at all if it is not relevant. So this is the second question, for which also the answer should be yes. If and only if the answer is yes to both these questions, that is, yes, the assumption is necessary, and yes, the assumption is also relevant for the class of problems that I eventually want to apply this model to. Only in such cases you should go ahead with that assumption. Otherwise, you'll have to see how without that assumption you can still model the structure, because modeling means that you are away from reality, and how close you want to go to reality is what our vision was all about. But in order to do that, yes, you do have to make certain assumptions. It's not that we can do it without making assumptions at all. Yes, you do have to make assumptions, even if you're using the variational asymptotic method and all the other techniques that we talked about in the previous slide, be it nonlinear domain decomposition or the concurrent multi-scale modeling or the what is the other one? The non-deterministic techniques that we talked about. Even when you're using all of these advanced techniques, you still have to make assumptions, because that's what modeling is all about. But you can reduce the number of assumptions that you make, especially those assumptions which are questionable, either from the relevance point of view or from the necessity point of view. Drop them, and then you would have something which is far more rigorous and far more accurate that you can eventually derive. Right? So let's look through some of these assumptions that we typically make. The first one is what is known as a material assumption. That is, essentially you're assuming something about the behavior of the material, and we are saying that it is elastic. And in many of the literature, this is referred to as the Cauchy elastic material. Being from the Berdichevsky school of thought, I don't like to give materials or certain things its name based on people. These have existed for much longer before these people came into the picture. For example, we don't call the variational asymptotic method as a Berdichevsky method, like we call Rayleigh-Ritz method or a Galerkin technique, etc. We believe that these are things that are something which is discovered by us. Just because it's discovered by us first doesn't mean we give our name to it. So, but nonetheless, the reason why I'm mentioning Kaushi over here is because many of you will be going through literature, especially for your papers for the introduction section. You have to write literature survey or to get information as the fundamental basis for building up your models or derivations. You will need certain things, and when you go to literature you will see this mentioned. So there are different kinds of elastic material. So elastic by itself, it came up for a discussion in answering one of Shravan's question or Kedar's question, where we talked about yes, the material follows a certain loading path and the same path for unloading as well, which essentially means that from a mathematical, that's from a physical perspective, you're defining elastic material that way. But from a mathematical perspective, what it essentially means is that the stress state at any given location depends only on the strain state. So it doesn't depend on anything else. Whether it depends on the strain state at that particular location or a small region around it, talks about what is known as local elasticity and non-local elasticity. Let's not get into that right now. We are focusing on local elasticity. That means that a stress state at a point, by which we mean, of course, all the stress components, which could in general be 9 components of that matrix once the coordinate system is defined. If the coordinate system is not defined, it's still a second order tensor that we are talking about as the stress, which is not still expressible in the form of a matrix. So there's a difference between a tensor and a matrix. A matrix is a representation of a tensor for a given choice of the coordinate system. If the coordinate system is not fixed yet, you still have it floating around as a tensor, just like a vector. This is if the pointed direction of this pencil is the arrowhead of the vector, and the magnitude is proportional to the length of this, and the direction is given by the direction in which the arrowhead or the pinpoint of the pencil is pointing. So then you essentially have a vector. Now this vector exists by itself even if I have not introduced any coordinate system associated with it. But once I introduce a coordinate system, then I can see what is its projection on this, what is its projection on this direction, what is its projection on this direction. So then I will call it, let's say, V1 along vector E1, V2 along vector E2, and V3 along vector E3, where E1, E2 and E3 are, let's say, unit vectors along these 3 directions that I have introduced. So now V1 E1 plus V2 E2 plus V3 E3, or what we call in short as VI EI, where there is an implied summation over the index I, then we are talking about a particular representation of this, or we can talk of it as a column matrix where we write it as V1, V2, V3 column matrix that you have over there. So in either one of these cases, this is one representation after fixing the coordinate system. But the vector by itself was floating around and well and good without this coordinate system or that coordinate system. The coordinate system doesn't have any implication on what the magnitude of the vector is and the direction of that vector is. It remains the same. So in that sense, your stress or strain at a particular point at a given instant of time, if it's a dynamics problem, is a second order tensor, and that second order tensor, we are saying that sigma is the tensor, and therefore we are indicating it with a double underline over there. That tensor is a function only of gamma, which is again double underlined to showcase that it is also a second order tensor. For vectors, we will use a single underline to show that they are first order tensors. So sigma is some kind of a function of gamma, and gamma is the only independent variable on which sigma depends. So at any given point in space or time, gamma is fixed, and therefore sigma is also fixed, irrespective of whether you are on the loading path or unloading path. Now you can see the correlation between these two definitions of the elastic material, where we were talking about a particular component sigma ij depending on a particular component gamma kl. How it was depending was that whether it is the loading path or the unloading path, it was coming back on the same curve, and therefore at a given value of these gamma KLs, which is of course for visualization, we are showing just one of those components here and one of those components over here, but essentially every one of those components in a stress depends on every one of those strain components, but it doesn't depend on anything other than the strain components. So that's essentially what we are talking about. So this is of course at a particular location in space, which is given by a certain coordinate system, let's say x1, x2, x3, or if it is just a position vector that we are talking about, just a position vector r that we are talking about with a single underline because it's a vector, okay, and that r in turn is a function of x1, x2, x3 and time, right, which is of course choosing a specific coordinate system. But even if we were not to choose any specific coordinate system, that vector r would exist, and that at a given r gamma is known, and if gamma is known, sigma is known. So even if gamma is not known, in terms of that unknown gamma, sigma can be entirely determined. So whatever that gamma is, the sigma can be determined in terms of that gamma. So that one-to-one mapping between the stress and the strain, that is, we are talking of still in a three-dimensional sense, that is the 3D stress and strain. That's why we are talking of three spatial components or independent variables like x1, x2, x3 as one of the examples. It could be y1, y2, y3 or z1, z2, z3. There are many different coordinate systems that you could take, and it's not necessary those coordinate systems are orthogonal in nature, or that they are let's say Cartesian in nature. They can be curvilinear, and they need not be making 90-degree angles to each other. The unit vectors involved need not be the vectors represented along each one of those directions as multiples of which you're going to represent your vector need not be a unit vector. So they need not be orthogonal nor normalized. They could be any arbitrary set that you want to choose, as long as they are not coplanar and collinear. So which means that two of the vectors, all three of the vectors are not on the same plane, or any two of the vectors are not parallel to each other. So as long as you have that in the three-dimensional space, you have a set which is kind of linearly independent of each other, and therefore you can express everything in terms of those entities. But essentially at a given point in space and time, you know the strain state gamma, and therefore you know the stress state. That's all that the elastic material basically talks about. And when we define elastic in this way, we are talking of a so-called Cauchy elastic material. It's attributed to the scientist mathematician Cauchy in terms of what this definition of an elastic material is. So as you see, even in this curve, I've drawn a nonlinear curve. So it's not that all elastic materials are linear. You could have a nonlinear elastic material. At the same time, you could have had a linear elastic material also, which is following the same curve both for the loading and the unloading, and that's also an elastic material which falls under the same category. So far we are not saying anything about the material being linear, but the fact that it is elastic, and the limit for many materials up till which the elastic limit will be maintained and up to which the linear limit might be maintained can be quite distinct from each other. So in other words, various possibilities are possible in terms of there being elastic, inelastic, linear and non-linear in a material sense. Is this clear before we go to the second?
Sir, I have a question.
Yeah. Go ahead. Yeah, please.
Is the converse of this equation true? I mean, we have defined stress as a function of strain. So for particular strain, there will be particular stress associated.
Yeah, excellent question, Nilesh. That's a good one. So yes, so this is a 1:1 mapping that we are talking about, and it is both ways. It works both ways. So in other words, given the stress, you should know the strain, and given the strain, you should know the stress. In other words, what Nilesh is talking about is whether this is invertible. In a linear problem, it is quite easy to say it is invertible because this is not a singular matrix that you would have, and you can invert it to get from a stiffness matrix into what is known as a compliance matrix. But in a nonlinear problem, such an inversion may not always be feasible, but at least in a numerical sense you would have, in the sense that you would may not have a functional way in which you can write gamma as some nonlinear function of gamma of sigma. But essentially this exists in the sense that given the components of the stress in any coordinate system, you should be able to determine the components of the strain at the same point at the same instant of time. So that is the 1:1 mapping that we are talking about in the case of the Cauchy elastic material. Clear, Nilesh?
Yes, sir.
Yeah.
Sir, and moreover to that, I have one question.
Yeah.
Is it possible that the slope of this test and curve is zero at some point?
Yes.
And after that, it is becoming negative.
Yes.
So there will be two strains associated with a single sigma, right? I mean,
That's correct. Yeah.
so,
Yeah. So then we are not talking about so you're talking about, let's say, this going like this, and where for a you could have two values of the strains, right?
yes, sir. Yes, sir.
Yeah. So it's not just the functionality that is there, but it's also should have. So it's a good point that you brought out, that you should have the uniqueness as well. So something like this is if it is still elastic, that is, even here, let's say if the unloading path were to bring about, but still at this particular location there is a uncertainty about how what actual value of the strain is for a given value of stress. So then you do not have a 1:1 mapping over there, whereas for any given value of strain you have a single value of stress. So this is the case that Nilesh is talking about. That still falls under this category of the Cauchy elastic material, but there are different types within that, and you have to have a way of defining this particular relationship in a set of two things, depending upon certain conditions or certain constraints of let's say gamma being above or below a certain value, beyond which this duality can happen, or uncertainty can happen in the stress value for a given strain value. Okay?
Yes, sir.
Yeah.
So that means in this particular condition,
Yeah.
first equation will be valid, but converse will not be valid.
That's correct. Yeah.
Okay, sir. Yes.
Anybody else? Any questions on this?
Sir, does these sort of material exist? I mean, what Nilesh has mentioned, that case where inverse does not exist.
Yeah, very good questions. I really like the way you guys are asking quite provoking questions. Yes, they do exist, and the reason is because the stress and the strain, remember, are not quantities which are characteristic either to the material or to the structure. These are things that we introduce as definitions by ourselves in various ways to simplify our overall derivation process getting simplified. So that is the whole idea, to simplify that. So which means that the stress can be defined in various ways. Some of you might be familiar with the first or second Piola-Kirchhoff stresses, the Cauchy stresses, the true stresses, and so on. Many different stresses are possible. Similarly, in the strains, the Green-Lagrange strain and Hinke strain, etc. Various kinds of strains are possible, and there's a 1:1 one mapping between them in terms of the conjugate for the power conjugates that you can have. So we will come to all of that a little later, giving actual examples and the actual definitions, etc. But right now, just to answer this particular question that you're talking about, whether such a material exists, yes, it can, if you are choosing the kind of stress and strain that are of that kind. And you would see that, in fact, when you actually do a uniaxial testing using an UTM in the lab and keep plotting the stress versus the strain, you can see some materials having this kind of a behavior. If you're defining the stress, let's say, for example, as, let's say, the force divided by the original cross-sectional area, whereas the original cross-sectional area could probably be shrinking. If it's a positive Poisson's ratio material, then the cross-sectional dimension is shrinking, and therefore the true stress may not be the stress that you're actually dealing with. So this drop that might be occurring is because you're dealing with a stress definition which is not a true stress definition. And if you take the actual area of that, let's say the specimen that you have over here, onto which you are applying the axial load F, and you're slowly increasing this F incrementally and using a strain gauge, you're trying to measure the strain at the mid location over there, and you would see that the strain is actually measured as a true strain, but what you're measuring as a stress, if you're dividing the force divided by the original area, cross-sectional area, then obviously you're not dealing with the true stress, and that could be one of the reasons why you could have a behavior of the stress strain curve in a particular way. When you deal with in the actual case, then you would see that the stress values would be much larger because the cross-sectional area has come down. The force is still the same, whether you're dealing with the original cross-sectional area or the actual cross-sectional area. The actual cross-sectional area has shrunk quite a bit, which means that instead of going this way, the stress strain curve would actually be going this way, slightly up. So that is essentially what is happening, and because you're not doing that, that's why it's coming down, and that's why you have in many situations this issue of at a given value of stress, you're having two or multiple values of the strain that are possible. Okay, Shravan?
Yeah, thank you, sir.
You're welcome. Okay, I think we've crossed the time, so maybe we'll go talk about the second assumption in the next class. Thank you very much. If anybody else wants to ask any more questions, I'll be happy to answer them. Okay, thank you then. We'll meet next Monday. Also, I would like to remind you of the next milestone, that is your 2-minute video that is due on April 12th, which is exactly, I think, 3 weeks from now. So please start working towards that as well. And that is not an independent thing that you're doing. The more important thing is the research that you're carrying out and the documentation that you're doing. In that process, as you understand these things better and better, you're going to make that video. And that 2-minute video is not just going to be you talking in front of the camera. It has to be some kind of simulation, or it could be over which you are giving the background voice talking, or having, let's say, captions coming down. Or it could be some kind of an animation which describes your problem and how you're trying to accomplish that. Some preliminary results which you have got by then, because April 19th is your presentation in which you're going to give an oral talk about what it is about. So this video should essentially convey within 2 minutes what your problem is all about, how you're approaching it, and whatever preliminary results you've got using some innovative techniques, which could be some kind of a cartoon, it could be some kind of a simulation, it could be just let your imagination run wild and make it as impactful as possible. That's what the video is meant to be. Okay, so you have any questions on that also, I would be happy to answer. Okay. Okay, thank you then. We'll meet on Monday.
Thank you, sir.
Thank you. Welcome. Welcome. Bye-bye.
मृत्युञ्जय मन्त्राः
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा मृत्यवे स्वाहा